Hello. In today's video, we're going to be looking at the pre-lecture material for Lecture 6. So Lecture 6 is one of our flipped classes. So we'll be working on the problems for what we're going to be talking about today. So Lecture 6, we're going to go over the rest of Chapter 21 and the beginning of Chapter number 3. So with Chapter 21, we got through all the way to carbon dating, and then the rest of it is just kind of information. So I'm going to very briefly go over all the things, and then I want you guys to go back and look through the type notes on the PowerPoint. But the biggest thing I want for you guys to understand at the end of this is energy from nuclear reactions. So that will go a little bit more in detail in class about, but the rest of it, just kind of read through the notes on the PowerPoint and you'll kind of understand it. It's all just information. So first thing, real briefly, we're going to talk about is measuring radioactivity. Okay, so whenever we have a substance that is radioactive, it is going to be emitting radiation. And when it emits that radiation can be tracked by looking at different types of substances or instruments that can detect that those particles, the emission of those particles, or the high energy radiation in waves. So we have stuff like Geiger counters. There are things called film badges. There's phosphor materials that are used. And radio tracers, and also these things can be used as radio tracers as well, because of that emission of radiation. So when we're looking at radioactivity, we have different units for these. So our units of radiation, we generally look at Curie, or the becquerel, and those are just two units used to measure radiation. We also look at microcuries and millicuries as well, but they're just looking at how many times the detector basically sees a radioactive species come in contact with it. So the instruments used, or devices, to measure radiation, so looking at these Curies and becquerels, are Geiger counters. So usually what most people are familiar with, the things go so that's going to be the most common type of meter for detecting radiation, but there are things called film badges. Film badges are worn, and you can see if someone who is in a lab that has radiation in there, how much exposure that they are encountering in that lab. And then we have phosphors. So the phosphors are going to emit light as they absorb radioactivity. Okay, so this radiation can also be used as radio tracers. So because these things emit radiation, you can look at them and actually visualize different areas of the body using these radioactive substances. So they're used to visualize areas within the body. So stuff like iodine-131 is used to look at the thyroid. You can look at iron-59 to look at red blood cells. technetium-99 to look at your heart, bones, liver, lungs. So a bunch of different radio tracers that can be consumed, and then when they're consumed they go to different parts of the body, and then those body parts can then be visualized through that radioactive decay of those substances. Okay, now the important part of this chapter, energy in nuclear reactions. So with nuclear reactions, a lot of energy is released, and it's based on Einstein's famous equation, E equals mc squared. So anytime you have a nuclear reaction, there's actually going to be a difference in our mass between the substances. So there's going to be a loss of mass. So we're not going to have conservation of mass in nuclear reactions. So there's no conservation of mass in nuclear reactions. You only have conservation of mass in chemical reactions. In nuclear reactions, we have the conservation of mass and energy. And that's really the actual thing. It's conservation of mass and energy. So if you have a loss of mass, it gets converted into energy. The only time we look at that loss of mass in chemistry is with nuclear reactions. Our chemical reactions won't have any loss of mass. So, if we have a loss of mass, that what we call mass defect will go into this equation. So this is our energy in joules. Our mass defect, so our change in mass between our initial nuclei and our end nuclei. And then C is the speed of light, which is going to be in 2.998 times 10 to the 8 meters per second. So as a note, joules are going to be kilograms times by meter squared over second squared. So when we put mass into this equation, we need to put the mass in kilograms, but our speed of light can be in meters per second, because we're going to square it, and that would give us our meter squared over second squared. If we have a negative, so our delta M is negative, that means our heat is released. And that's what we're going to have in these nuclear reactions. We're going to have a release of energy. For instance, if we have uranium-238 going to thorium-234, we're releasing an alpha particle in this process, but the change in mass associated with this process the change in mass in this process is negative 0.0046 grams. Not a lot, but there is a change in mass. So there is less mass at the end of this reaction. Because of that, we can take this value, put it into Einstein's equation, putting it into kilograms, and then putting in our 2.998 times 10 to the 8 meters over second, squaring that, and what we get is a delta E equal to negative 4.7 1 times 10 to the 11 joules. That is an amazing amount of energy. So if we have 1 mole of this substance, it's going to release this amount of energy, where 1 mole is equal to 6.022 times 10 to the 23rd atoms of uranium. And we'll talk more about moles in this next chapter. But just know that this many atoms of uranium will release this amount of energy when uranium goes from 238 to thorium-234. Okay, so the reason we have this mass defect is because we have the individual particles in our nuclei. They're going to be less, or the more massive than the nuclei themselves. Sorry, are more massive. Than the combined nuclei. And you can see that if we look at any sort of nucleus, if you mass up their individual nucleons, so their protons or neutrons, and you look at their mass versus the mass of the nucleus itself, and there will always be a mass defect. So the difference in that mass is called that mass defect, and it's basically you have the mass of all the individual nucleons, and then you put them together and they bind together, and they need that energy to bind together. We call that the nuclear binding energy. This is the energy needed to bind the nucleons together. So we have mass defect, so that loss in mass being converted into our nuclear binding and energy. Okay. Now I'd like to talk about fusion and fission. So, taking the idea of that binding energy and that mass defect and getting energy from these things. So, when we have nuclear fission, this is what we have in nuclear power plants. Nuclear fission is going to be the splitting apart of a heavy nucleus into lighter nuclei. And, of course, any one of our nuclear reactions will cause a lot of energy to be released. So, uranium-235 will do this when it absorbs a neutron. So it absorbs a neutron, and so let me write this a little bit differently. That uranium splits in half into tellurium and barium. Or sorry, tellurium and zirconium, or barium and krypton. So I can go one of these two paths, and then each one of these will produce additional neutrons. So a neutron comes in, hits the uranium, then uranium splits apart either in tellurium and zirconium or barium and krypton, and then it releases a whole bunch of energy. So the breaking apart of uranium-235, this process releases 3.4 times 10 to the 8 kilocals per gram. And this is versus something like natural gas, which is 13 kilocals per gram. So 3.4 times 10 to the 8 versus 13. Significant difference. Okay, so when this occurs, when this fission process occurs, it breaks down and it produces more nuclei, or neutrons. Then those neutrons can go ahead and hit more uranium, and then they will do the same process over and over again. And we call this a chain reaction. If we have a large enough amount of that uranium-235 that it will continue the process. So if there's enough 235 uranium, we have a chain reaction. So each fission reaction will give more neutrons, which will hit more fissile material, and will continuously break apart into neutrons, and those neutrons will continuously hit more uranium-235, and this is how we have a self-sustaining nuclear fission reaction. Now, they have what's called a critical mass. A critical mass is when we have enough to have that chain reaction. And then if we have greater than that critical mass of uranium-235, we have what's called subcritical mass. That is a bomb. So if we have, supercritical mass. So subcritical mass, no chain reaction. Maybe a couple reactions will occur, but then the neutrons are going to escape the uranium area. Critical mass, we get a chain reaction. So we can have a self-sustaining nuclear reaction, and that's how nuclear power plants work. And then a supercritical mass, we have too much uranium-235, and this results in a bomb. So a nuclear bomb, if you've heard of nuclear bomb, this would be a nuclear bomb. But nuclear power plants, they're going to have a critical mass of uranium-235, and what it is you have uranium, and you have some uranium-235 throughout. So, and that's the fissile material. And the rest of it (238) uranium. So it's enriched uranium it's enriched with 235. The 238 is the more abundant, and it's not a fissile material. It is radioactive, but not fissile. And then we also have fusion. So fission is how nuclear power plants work. Fusion is the sun. That's how the sun works. The sun takes two light nuclei, combines them together into a larger nucleus. And this is extremely powerful. It releases a lot of energy. So it's something like 5.3 times 10 to the 8th kilocalories per gram. So it is a lot of energy that's released here as well. And this is done with hydrogen, so it's a lot cleaner energy-wise. But it's a lot harder to do because of the extreme experimental conditions that it has to be done in. So think about the sun. It has to be like the sun. 1 times 10 to the 8th degrees Celsius, very, very high, and 1 times 10 to the 5 atmospheres. So in order to get fusion to occur, you have to have incredibly high temperatures, incredibly high pressures. Okay. There's more information on the PowerPoint if you want to look at anything about radiation in the environment. I'm going to end this particular video here and then do an additional video for the beginning of Chapter 1. Okay, sorry, Chapter 3. And that's everything for the end of Chapter 21. Please look through those notes. We'll go over calculating out the mass defect and nuclear binding energy in class. But that's everything for Chapter 21.